All right. So last lecture we actually started defining work, and we pulled in essentially the definition of a force doing work and how force acting across a distance will actually give you some amount of work out. So this time we're actually going to keep pushing forward with this idea. We're going to look at forces and work, and then we're going to relate this to potential energy and actually talk about conservative and non-conservative forces. So we could ask the question, what is the work done by gravity, because that's a force, on an object sliding down a frictionless path? Okay, so for now, it's important to note that the path we're talking about is frictionless. Okay. So we can use this definition of work to answer that, just like we have been doing. It's just going to be the force times the distance that this thing goes. So we can plug things in. We have the work done by gravity, and then we have the force due to gravity, and of course it could be a dot product, like we talked about, with that displacement vector. Okay, you could do the dot product if you want to, or you can just remember that it's simply the magnitude of the force and that displacement times cosine of the angle between them, because the dot product really is just that projection. So if you can't quite remember, we could actually talk about it very quickly. So essentially, the dot product is just going to project the result of the dot product is just that projection of one vector onto the other. So here it'll be the projection of F onto the displacement. So we do want that parallel piece, the parallel component of force to the distance that we're going. Okay, well, notice in this first part here where I said the work done by gravity on an object sliding down a frictionless path, I didn't really say what the shape of the path is. So let's look at the picture over here. You can see we have just this randomly drawn path where it starts out with a little slope, then gets really intense, and then cuts out at the bottom and becomes level again. So we have a wonky path, and we want to calculate the work done by just gravity. All right, so gravity is always going to be pointing down. Then we just need to sum up all the little increments of work across this. So the issue here is that this angle, as you can see in this little blown up area here, the angle here, angle theta, well, that's going to be changing depending on where you are on the path, right? If you're down here at the bottom, well, that angle is going to be 0. No, sorry, that angle is going to be 90 degrees because we're looking at gravity down, and then the path is going to be directly to the right. Same thing at the top of the hill up here. That angle will be 90 degrees there. And then as we're traveling down this path, that angle is going to be changing depending on the path. So that's something we need to think about. So to do that, let's just think about the work done over a really small distance. Okay, so we're just going to call it this little infinitesimal dw, okay, for the work done by gravity over a little piece. Okay, now if we do that, we need to think about this. So we want a really tiny displacement, a little, just very tiny piece. Okay, so this is essentially going to come to the magnitude of our force. Okay, now we usually write those little infinitesimals as like a ds. So my displacement will just become the ds, and of course we'll have the cosine data there because we're projecting with the dot product. Okay, so that's where these pieces come from. So what's interesting is we can actually, from the diagram, we can rewrite this small change. We can rewrite this cosine theta ds. We can rewrite this as something else. So if we look back at the diagram, we notice here that this angle, well, that's also theta, the one I just drew in orange. Okay, so we have our hypotenuse, which is ds, and then if we were to take the cosine of ds, or cosine of theta times ds, so that's going to be the hypotenuse times cosine. Well, that's going to give us the adjacent piece here. So it turns out, really, this is just the trig identity. The hypotenuse ds times cosine theta will just give us this vertical adjacent piece dy. So we can just do a straight up substitution and say, well, this, if we attach a negative, we could say negative cosine theta ds is simply just the same amount as that change in dy. So the cosine ds is just the vertical change. So we can actually rewrite our little infinitesimals here as the change, small change in work equals a negative mg dy, okay? So just be aware and remember that this is just, we use trig to write this differently, but this is still just the cosine theta ds, right? We just use the trig of the problem to rewrite it. Okay, so now we have this new statement. We have dw equals negative mg dy. So what can we do with that? Okay, well, it's actually, we can integrate it. We have infinitesimals on both sides. So if we integrate the left-hand side, dw is just w work done by gravity. Now, remember that negative mg, those are constants. We can pull them out front. Now we can just integrate across dy. All right, so now this is an easy integral. We're just integrating the constant in there. And so it turns out we're just going to have the constants up front. We integrate essentially over a value of 1. So we wind up with y final minus y initial. And it turns out the work done by gravity is simply negative mg times the change in height. So notice that this just depends on height. So the work done by gravity is independent of theta. It didn't care that the force vector and the displacement vector were constantly changing. That went away. We could make that go away. So it turns out the shape of the path does not matter. That's super important. Okay, if you look over here, the work done by gravity is the same in all 4 cases. I mean, we have some crazy paths. We have one simply just goes straight down. We have one that does some weird stuff here, and then one that sort of takes an arc. So in all these cases, because the path doesn't matter, work is the same. And that's pretty cool. That's a pretty cool result. That'll come in handy several times throughout the rest of the course. Okay, so let's talk about what just happened and let's give it a name. So the force due to gravity is actually a conservative force. Okay, and a conservative force is essentially a force that doesn't depend on the path taken when calculations are being done. Okay, so remember that potential energy. Remember that potential energy is an energy of position. That's important. So the system has, so if we look at this arbitrary picture over here, this system has some potential energy at A and some other potential energy at B. Okay, so we can actually calculate the change in potential energy regardless of the path taken. So that's simply just the difference of the two. It doesn't depend on the path taken, okay? Of course, while this arbitrary particle, which it could take path 1 or path 2, while it's doing this, you'll remember that if we change the potential energy, we're also changing the kinetic energy, right? We're going back and forth between these two. So potential energy is transformed into kinetic energy, since the change in kinetic energy equals the negative change of the potential. So if you're losing potential energy, you're going to gain kinetic energy. Now, we've shown in the previous slide here, we've shown that work done by gravity, or at least a non-conservative, or a conservative force, is independent of the path. So here in this case, If the potential energy here is independent of the path, like it says here, right? So if it's independent of the path, well, that means since they're related, the change in kinetic energy must also be independent of the path. So essentially, no matter the path taken, the object will have the same kinetic energy at B. Okay, so we have potential energy down here. We also have some kinetic energy. And up here we'll also have a different kinetic energy. So the idea here is essentially if the path doesn't matter, obviously we can just calculate the initial and final potential energies, but that applies to the kinetic energy as well. We can even push this further. So since potential energy and kinetic energy are independent of the path, we could even say, well, since work and kinetic energy are related, well, that means the work done by the force is also independent of the path. Okay, so work done by a force is also independent of the path. So here we have potential energy, kinetic energy, and work. For conservative forces, we'll talk about non-conservative forces later, but for right now, all three of these do not depend on the path. Okay, so any sort of path independence, that just indicates that it is, in fact, a conservative force. So we have a trick here to know when a force is conservative or not. So the idea is a potential energy can be associated with a conservative force. Okay, so since we have a gravitational potential energy, okay, that tells us that gravity is a conservative force. Okay, so other forces, which we'll get to in a little bit, that are non-conservative, like friction, we don't have like a potential associated with friction. We do have a potential associated with gravitational potential energy. And if you think about it, we also have a force which is Hooke's law. Well, it is a conservative force because we can calculate a spring potential energy, right? So we could talk about, whoops, not an M. There we go. We could talk about a spring potential energy, which we've done before, which is 1/2 kx squared. So let's actually think about what's going on here. Let's take that spring force, Hooke's law, and dump it into our definition of work. Okay, remember, it looks a little cluttered here, so I'm just going to write work equals the integral of F ds. So here, this extra notation is just saying that we're moving the spring from some initial position to a final position. All right, so we're going to plug in that force. We can make it a little easier. We can just say, well, let's assume that the spring starts from equilibrium. Okay, so our equilibrium position is just 0 meters. Then we can actually say, well, okay, the delta x can really just be written as just an x. That way everything's in reference to the equilibrium position, and then we don't have to worry about having those two terms floating around. Okay, so if we do this, we can plug in Hooke's law. Okay, well, the k comes out because that's simply a constant, and then you guys should be able to integrate this pretty easily now. So when we do the calculus here and integrate, notice what we get. We still have the negative out front, so be careful with that. Now we have a final potential energy, because that's our definition. I just wrote it up here. That's our definition of potential spring energy, or spring potential energy. Okay, minus some final or sorry, minus some initial potential energy. Well, that we can actually just rewrite. That is our change in spring potential energy. Right, this basic calc problem, and then what falls out of that, we start with the force, but we integrated. Turns out we actually get the statement of the change of potential energy. Right, there we go. So this is interesting because now the work done by a spring, ooh, I'm running out of room. The work done by the spring is just the negative of the change in its potential. So notice we start with the force, we were able to find and relate a potential to it, and because we can do that, we can calculate the work with the force or the potential, and we also demonstrated that this is a conservative force because there's a potential related. Okay, so we went from force to potential energy. Now the question is, how can we go backwards? Okay, so let's say we want to go backwards. From potential energy to finding a force. Okay, so let's rewrite some things here. So if we wanted to find the force provided by a potential energy, well, we know that work done is just the force times the distance that the work was applied. And we do know, especially from the last couple of slides, that work also equals that negative change in potential. Well, that must mean these things are related somehow, the force over the distance and the change or negative change in the potential. So let's set these equal to each other. I mean, they're both work. We said this was work, this was work. So they're technically equal to each other. So if we do that, what we can do is rewrite this. We can just divide the delta S over. Okay, well, that looks a whole lot like a derivative. So if we divide that delta S over, and then we make our increments really, really tiny and get those infinitesimals, well, it turns out that the force of the spring really is just the spatial derivative of the negative of the change of potential, or the negative spatial derivative of the potential, right? So however your potential changes with distance within space is going to tell you what your force is doing. So the force is the negative of the slope of the U versus S graph. You can see over here just this simple example. We have GPE, gravitational potential energy. Okay, so as the height increases on the x-axis, so do keep in mind this is actually something getting higher. As that height increases, obviously our gravitational potential energy increases. Okay, now this plot is simply just right here. This plot is mgy. That's the equation of the line. Okay, now if we take the derivative du dy, well, mg are constants, they come out, and look at what we're left with. We're left with mg. Well, that's certainly force due to gravity, but remember, okay, so we took the derivative, now we have to apply the negative out front, right? So the way you calculate this is negative du dy. So if force is the negative slope, there's our force due to gravity. So this is a really interesting result here, where a lot of times if you have equations for energy, you can take the derivative with respect to a distance, and then it suddenly becomes a force problem. You get all the forces out of it. You can see down here, panel B, if you're interested, the slope of this linear relationship here, as you well know, is constant. So when we actually take the derivative, we just get negative mg. And that's constant, it stays constant. So that's what's going on in the second panel. But the main thing here is just to realize that force equals negative du ds. That's quite important. Okay, now let's hit non-conservative forces. So not all forces are conservative. I've been hinting at that. So let's think about friction now. So if we consider the work done by friction on a particle across a small distance, okay, so we're using our small distance infinitesimal trick again. Well, okay, small work over small distance. That means we're going to look at the infinitesimal small differential W equals F force due to friction, and that's going to be multiplied by our teeny tiny little vector ds. Okay, well, that's going to be the magnitude of the force due to friction. That's just mu k mg. We've calculated that before and talked about it in previous lectures. Now our distance, right? So this is still our F. Now we need our delta R. Well, we're using infinitesimals, so that's going to be a ds. And then maybe not necessarily a theta. We're going to keep it general, so I just use cosine alpha as the angle between these two vectors. So maybe we have force this way, and then the displacement is this way, and that angle is free to change. Now, here's the trick. Here's where we can think about this conceptually and mathematically, okay? So remember, the direction of the friction vector is always opposite the direction of motion. Okay, so depending on the direction of motion, that is going to dictate where our friction vector points, okay? Clearly, because the definition of friction says it's always opposite, friction depends on the path taken, okay? You have to know what your path is doing so you know which way to point your friction vector. And that's what this is saying here. All right, now this destroys our definition of conservative forces, right? Because the conservative forces don't care about the path. Friction does, therefore friction is non-conservative. Now, that was just us thinking about it conceptually, just saying, well, if friction depends on the direction of the path, so we know which way to point the friction vector, then it's got to be non-conservative. So let's think about it more mathematically. Okay, so we can look at our original statement here, and of course we can integrate it. Can't really change the ds to anything, because if you look at the geometry of the problem over here, there's not really a way to rewrite it in terms of something else. There's no like other dimension where we can rewrite it in dy or anything. So this is just a top-down view of what's going on. So that means we could just try and integrate. And remember, an integral is just a fancy summation. So we're literally just going to sum across the whole path. Okay, so we plug things in. There's our force. There's our dr. Okay, we pull the force out because it's constant. Now we just have to integrate here. Now, since we are summing, let's take a look at the picture over here on the right. So if we go across the first path, okay, and we sum up all these chunks, we go to the start to the end, we can sum up all those chunks and we get some sort of ds, right? Some change in distance. Now, if we integrate across the second path, notice that if we integrate across the second path in green, there's more chunks to add up. So our delta S will be bigger, okay? So the delta S from the green path is larger. Just because we're having to add up more little infinitesimals. So when we integrate across a path, friction is definitely path dependent, okay? So a force that depends on the path, ds, taken is called a non-conservative force, which we sort of defined up there, but this is the general statement, any force that depends on the path. So a potential energy cannot be defined for a non-conservative force. That's another thing here. We have no potential energy equation for friction. And then energy can't be recovered if it's a non-conservative force. So we have no place to store it. So if we lose it to a non-conservative force, it's gone. We can't get it back and store it somewhere. Okay, well, so we've talked about mechanical energy before, where that's just like kinetic plus potential, and then that's the mechanical energy of the system. But both conservative and non-conservative forces can do work and can change the mechanical energy of the system. Okay, so we do have conservative and non-conservative forces. So the net work responsible for changing the system's kinetic energy, remember the work kinetic energy theorem? It's right here. So that net work, remember this is just the sum of all the work. Well, to come up with that, we have to include our conservative and our non-conservative forces. Both of those go into the net work because it's net, it's total. So the work done by conservative forces can now be associated with a potential energy. Okay, we know that, we just showed it. So what we can do, we can actually rewrite the work kinetic energy theorem. So what I'm going to do is I'm going to replace, essentially, from up here, I'm going to replace WC with the negative, the change of the potential energy, and then move it over to the other side. So what I'll do is briefly get rid of this, and you'll see that where there was a plus W, where there was a minus W, because it's the negative of the potential, I just added that over to the other side. Okay. But now remember the kinetic energy plus the potential energy. Well, we've already defined that to be the mechanical energy, so it turns out this is the statement we're after. So any change in the mechanical energy is equal to the work done by a non-conservative force, okay? So if you think about it, remember we talked about how the mechanical energy in an isolated system is always conserved. So kinetic energy and potential energy can swap with each other. We can have internal thermal energy. That total mechanical energy stays the same if the system's isolated. As soon as we have interactions with like friction, right, non-conservative force, that's when we start draining energy out of the system. That's when the total mechanical energy changes. So that's why I've boxed this here, and it's super important. The big overall changes to the system's mechanical energy happens with the environment, and those are usually non-conservative forces, like friction. Okay, so mechanical energy, like I said, is conserved if there are no non-conservative forces. So an isolated system, mechanical energy is preserved. Okay, now let's get to some thermal energy here. Everything we've talked about so far has been mechanical. So let's look at what's going on with some thermal energy, and then we'll look at a conceptual example, and we'll call it. So mechanical energy deals with the macro physics of the system. Okay, so this is the large object, you know, like the baseball traveling through the air, or the whatever's happening. Maybe you've got a big flywheel that's spinning on a car. So the mechanical energy deals with the macro physics. Okay, so this is just the idea of large objects. You can see that over here on the right. So the macroscopic motion of the system as the whole. So M is my system. It's the whole thing. This whole big clump has some sort of velocity. It's moving to the right. That's what we're talking about here. Okay, well, that's mechanical energy, but thermal energy deals with the microphysics of the system. Okay, so like the heat retaining bonds within the objects of the system, or the object itself. Okay. So now we're going back to that whole like balls on springs to model molecules. Okay, so we're going to zoom in. As you can see in the bottom right hand side, we have all these little molecules, all these springs. And essentially what's going to happen is we're going to talk about the kinetic and potential energy down here at the micro scale, and then relate that back to the kinetic and potential energy at the macro scale. Okay, so the total kinetic energy of all the atoms at this microscopic level is K micro. So we have a K micro in here. Okay, we also can store potential energy in these bonds. So we also have a U micro. So do note that the subscripts here are micro. We're talking about what's going on inside the object. So the total thermal energy is just the sum of these two. So we have the kinetic and potential energy at the microphysics level, and that's our thermal energy, total thermal energy. Now, if we were to sum up the energy across all the atoms making up an object, that's actually a lot of energy. We're talking like 0.12 megajoules, okay? So that's like roughly like 1 or 0.12 times mega is what, 10 to the 6 joules. So there's a lot of energy in these objects already that doesn't necessarily affect their overall motion. Okay. So now let's talk about how these micro energies and macro energies actually affect each other here. So if a book is shoved across a table, obviously it gradually slows down and it eventually stops. So if I give something a shove, you all can do this right now on your desk. It's going to slide a little bit and stop. So the big question is, where did that kinetic energy go? So what's going on here is essentially molecular bonds get stretched on both sides of the boundary. Okay, so we have bonds on the desk or on the table, and we have bonds on the book. Okay, as they slide against each other, they actually get stretched. They form temporary bonds that get broken, and then those temporary bonds, as they break, they actually cause some vibrations in both objects. Okay. And that vibration is actually just the added kinetic energy from the sliding. You can see that over here on the right-hand side. We've got the zoomed in microscopic edges of like the surface of the book and the table. So we have the book up here, we have the table here. So we got like this push going on, and you can see that there's temporary bonds being made, but they're really weak. And as the book keeps going, those bonds are made, but then they're essentially immediately broken. But what it does is that does cause some jiggling in the lattice structure at the molecular level. So you can see we've got some extra jiggling here on both sides. So the book and the table both get some energy out of this, okay? So what's going on essentially is we have atomic interactions at the boundary, okay? That transforms the kinetic energy of the moving object. Okay, so this is going to be K macro. So the kinetic energy of the big object overall, well, that gets transformed into thermal energy, the micro kinetic and potential energy. So we're going from the macro overall energy of this everyday object down to the molecular level. Both objects, like we said over here in the bottom right, both objects get a small temperature increase because those atoms start moving even more. Okay, so this is perceived as a temperature increase for both objects. So forces, just like you'd expect, forces such as friction and drag, they actually cause the macroscopic kinetic energy of a system to be dissipated as thermal energy. So again, we have this K macro going to E thermal. And of course, friction, non-conservative, drag, well, there's no potential energy associated with drag, so there's another non-conservative force. So if you extend this, it turns out that dissipative forces are always non-conservative forces. Of course, dissipative forces always increase the thermal energy, and they never decrease it. So it's the whole idea of we're losing energy to somewhere else. We can increase that thermal energy, but we can't get it back. We can't store it anywhere, therefore non-conservative. Okay, let's look at this conceptual example really quick. So consider a box being pulled at a constant speed across the floor. Okay, so we're not accelerating or anything, just a constant speed. Both the surface and the box, okay, they get warmer due to friction. So we're moving at a constant speed, so we have some sort of K macro. We have a macroscopic kinetic energy, but the surface that's the box is sliding across and the box itself are getting warmer. Let's see, we had K macro. Okay, and then we do have the box getting warmer, which we said was going to be E thermal. Okay. but the kinetic and potential energy remains the same. Okay, so here's a good thing to think about. So the kinetic and potential energy, there's no change in the kinetic energy. There's no change in the potential. The box isn't speeding up or slowing down. The box isn't moving up to gain gravitational potential energy. There's no springs, so there's no increase or decrease in potential energy. Well, so now the question is, where is this heat coming from? It's not coming from kinetic energy. It's not coming from potential energy. So what is the source of E thermal? Well, we don't know yet. We have to do some math because clearly it's not coming from kinetic or potential energy. So remember that work is just energy transferred to a system by the environment. So the force from the rope is part of the environment, right? We're pulling this box across the floor with a rope or, you know, whatever string. There's a picture down here at the bottom if you'd like to see it. So the source of this push or pull is actually adding energy into the system. Okay. So if the force from the rope is part of the environment, external, it is the source of the increase of the energy of the system. Okay, well, we know that the thermal energy is increasing, and thermal energy increases from work done on the system. Well, the rope, the tension of the rope, that's the force here, right? That's our force over some distance. Okay, so it turns out what's going on is the thermal energy in the system as it's getting warmer. We're not getting that from the kinetic energy or the potential energy inside the system. It's actually coming straight from that outside pull, that outside, the box being pulled. That tension from the rope is where that thermal energy is coming from. Now we can rewrite this tension since it's T delta S. Well, the tension and the friction, remember kinetic friction always opposes the motion. And since there's no net force, it's a constant speed, we know that the tension and the friction have to equal each other, right? There's no excess force, there's no net force. So we can actually rewrite this one more time. So it turns out E thermal, going through the step of relating it to tension and then relating the tension to friction, that's where our energy comes from. We're actually getting the thermal energy from the friction over some distance. Okay, so there is no energy transfer between the box and the floor. Energy is transferred to both from outside the system, right? We're getting this energy from the rope and the rope being pulled, and then that box in turn sliding and generating that friction. Okay, so here I do want to point out things to think about. This is an interesting thing here that people might think, oh, well, you know, the box is moving, so therefore the thermal energy is actually coming from the kinetic energy. No. Well, maybe there's stored energy somewhere. No, not at the macroscopic level. So it's really interesting to think about. So even though that according to this one equation, delta K plus delta U equals 0, according to our mechanical energy, which is not changing, the box shouldn't be heating up. So we have to look outside the system with the thermal energy to see where it's coming from. So the non-conservative forces outside, the external work being done, that's actually coming from the rope. So just a quick summary, if my slide will change. There we go. So potential energy is the energy of position. I think I've said this several times, but it's always good to keep in mind. Kinetic energy is the energy of motion. Okay, so here we have like a delta Y for the potential energy. Then we have like a delta V, or a change in velocity, for the kinetic energy. Conservative forces can be related to a potential. Okay, conservative forces can be related to a potential. I have gravity listed here because we have mg delta y. Hooke's law, which we talked about, we have 1/2 k delta x squared. We can also relate that force to a potential. Those are always conservative forces. Work done by conservative forces is always path independent. So we never care how the object gets from point A to point B. The work done is the same if the force is conservative. However, non-conservative forces have no related potential. Okay, so like friction. And of course, they are path dependent. And then finally, work done by external forces can raise the temperature of the system. Okay, so we showed that in the previous slide, where we had the work done by tension was going into E thermal. And we also related that, well, the work done by tension is the same thing as just friction, also going into E thermal. All right, so that's summed up essentially how we can think about force, work, and potential energy and relating all those together. So with that, I'll end it here, and then the last lecture will actually tie up a few things and then look at some examples.